What's up, guys? This is Jahangir from MedPorium, and today we're going to be talking about the standard reduction potential, what it is, and how to actually calculate it. So first, let's start off by what that even is, what standard reduction potential even is, and it's denoted by this E and to the degree thing. So this is our standard reduction potential, and you can search up a definition because I think the definition is the standard reduction potential is the potential when the ion concentration is 1 molar and the gas pressure is 1 atmospheres. But you really don't have to know the strict definition in order to answer these questions, because the only equation you need to know is that the standard reduction potential of the cell equals the standard reduction potential of the cathode, so cathode, minus and I'll just copy this because I just feel too lazy to write it again. So it's going to be the standard reduction potential of the anode. So that's pretty simple. You just need to know this equation in order to solve those questions. But there are a couple things you need to know in order to solve some of these questions. So one of the things you have to know is that a greater, and I'll put E cell, or just standard reduction potential, is going to be, and I'll just change this color here, our cathode. Now you might be wondering, well, how do we even know that? Well, if we read the definition, standard reduction potential, a higher standard reduction potential means that we're being reduced. That's pretty much what it means. And we know from our acronym REDCAT, reduction occurs in the cathode, so a greater standard reduction potential is going to be our cathode. So what about a smaller standard reduction potential? So I'll just copy this. So with a smaller standard reduction potential, this is going to be our anode. Reason why is because if we have a smaller standard reduction potential, this is going to be oxidation. We remember from our acronym NOx, in the anode oxidation occurs, so we know that a smaller standard reduction potential is going to be our anode. Now, another one of those conceptual things you need to know is that a positive standard reduction potential means that products are favored at equilibrium. So products are favored at equilibrium. And if we have a negative standard reduction potential, then our reactants are going to be favored at equilibrium. So those are some of the conceptual things you need to know before solving those questions. And now let's actually dive into a couple of those questions. So for this example, let's say we have copper 2+, and I'm not going to write the gas states or the physical states, plus our electrons equals Cu. So as you can see, when we add those electrons, we add 2 electrons, canceling out that positive charge, so we're going to be neutral. And for this example, our standard reduction potential is going to be 0.34 volts. Now, on the flip side, on our second reaction, we have zinc 2+ plus 2 E, 2 of our electrons, and that goes to zinc, and our standard reduction potential for this one is going to be negative 0.76 volts. So first off, we want to find which one is pretty much being oxidized, which one's being reduced. So we know that a higher standard reduction potential is going to be one that's reduced, and we know that a reduction is a gain in electrons. So all we have to do is just leave this as it is because this is a reduction. But over here, since we have a smaller standard reduction potential compared to this 0.34, this is going to be in oxidation. So what we have to do is to make our complete reaction, we have to switch these out because we're going from a loss of electrons. So this is what our sort of half reactions are going to look like. Those electrons will cancel out, and what we have as our final sort of equation for the reaction is Cu2 plus Zn, or zinc, goes to copper plus zinc 2 plus. So we cancel out those electrons. But one thing to note with these standard reduction potentials is even though if you flip it, you double it, you add something, it doesn't change these numbers. So this isn't applying Hess's law, because Hess's law doesn't apply to the standard reduction potential. We still have the same standard reduction potentials. We just flip the reaction in order to get our final reaction with these half reactions. So now that we know that each cell equals cathode minus anode. So we ruled out that this 0.34 was in reduction. And red cat, we know that that would be the cathode. So 0.34 is our cathode. So 0.34 minus, this is our anode. So that's negative 0.76. And that would equal 1.1 volts. And that is our answer for the standard reduction potential for this equation. If that was confusing in any way, let me break down a little bit more simply. So we have two half reactions. The first thing we need to do is to get our overall reactions. And obviously we need to cancel out these E's. But looking at, or these electrons, but looking at our standard reduction potential, this helps us understand which one is being oxidized, which one's being reduced. So first thing you want to do, look at your standard reduction potentials, and if it's a higher standard reduction potential, it's being reduced. If it's smaller, then it's being oxidized. So it's simple to understand, and since we know that over here, the standard reduction potential was being oxidized, we know oxidation is a loss of electrons. So we need to write an equation that satisfies oxidation, which is this equation, because we lost electrons. And when we're losing electrons, the electrons go on the product side. When we're gaining electrons, the electrons go on the reactant side. So that's a very important thing to know. We get our final reaction over here, and we just calculate our standard reduction potentials, looking back at our equation over here, which was the standard reduction potential of a cell equals cathode minus anode, or just remember it's just cathode minus anode. And we know red cat and ox, the reduction is with the cathode and oxidation is with the anode. So it was 0.34 minus negative 0.76, and that got us 1.1 volts. Now let's do another question, but let's look at something like Ag plus E minus, or the electron, keep saying E minus, just make it simpler. And we have that, so zinc 2 plus 2 of those electrons goes to zinc. So right off the bat, oh, and actually let me write those standard reduction potentials. So it's going to be 0.8 volts, and another one is just going to be negative 0.76 volts. Let me actually write this better. So we're pretty much using the same values for zinc. And on any practice exam, you're always going to be given your standard reduction potentials, because you're not expected to know every single standard reduction potential for every reaction. So you're given that, thankfully. So our first thing we need to do is identify which one's being reduced, which one's being oxidized. This zinc, we obviously know is being oxidized because it has a smaller standard reduction potential. So all we have to do is switch these sides over here. So this would be maybe right here. We have our zinc converting to zinc 2 plus those 2 electrons. But look, we have 2 electrons on this side, but only 1 electron over here. So what we have to do is multiply this by 2 in order to get our 2 electrons. And when we multiply by 2, I'm just going to say we did, we'll move this 2 over here, copy paste, move this 2 over here, and do the same thing for over here. Those 2 electrons cancel out because that's what we want. We don't want electrons in our final overall reaction. So this becomes, let me draw a straight line. This becomes 2Ag plus zinc goes to 2Ag plus Zn2 plus. That's zinc 2 plus. And this is our overall reaction. But now we need to find the standard reduction potential of the overall cell, which is cathode minus anode. So this was our reduction. This was our oxidation. So red cat, 0.8 minus negative 0.76, which gets us 1.56 volts. So another thing to remember, even though if we multiply 2 on the reaction side, those half reactions, that does not affect our standard reduction potential values. That doesn't affect them at all because we still use cathode minus anode given any of these, and that's how we find our standard reduction potential for the cell. So hopefully that helped you guys in any way, and as always, a Pomodoro a day will make you a doctor someday. I'll see you guys in the next one.